My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda and YouTube channel. So I'd like to welcome you all to our International Physics webinar. So good evening to all here in Bangladesh and a very good afternoon to all those who are watching this program live from UK. So hope you are well and safe from Corona pandemic. So today it's our 136 International Physics webinar. So we are all know that we are staying in a Corona pandemic situation, so we cannot continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And today it's our 136 international physics webinar. So we are trying to adjust with this new normal situation. So today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, Ohio State University, Athens. And we have with us here today Dr. Nancy Sandler, Professor, Department of Physics and Astronomy, Ohio State, Athens. And she has already connected with us. So I'd like to welcome our speaker. So good afternoon, madam, and welcome to our International Physics webinar. So it's our pleasure to host you in our International Physics webinar, madam. And thanks for accepting our invitation.
Thank you. No, thank you very much for inviting me and for being so patient until I could find time available to prepare this talk. So I really appreciate it. So let me go and start.
Yeah,
before I get into the talk per se, I want to tell anybody who wants to ask questions. I don't know how questions work in this format, but
at
interrupt
the end,
me.
Okay, so sorry, madam. So at the end, we have a discussion session. Anybody can join, and if anybody want to ask question, they may also ask question by commenting in Facebook and YouTube. So you can carry on.
Okay. So in case I become unaware of the questions, just make me notice it. Okay. Okay. Perfect. Thank you. Thank you very much. So before getting into the topic of the talk, I just wanted to introduce a little bit the place where I am, where I work, where I live, really. And this place is Athens, Ohio. Athens is, so this is a map of the state. This is the typical way in which we divide the United States. We talk about the West, the South, the Northeast, and the Midwest. And these are the states that make the Midwest. And this is the state of Ohio. And, oh, why is going so fast? And this is, let's go again. This is where Athens, Ohio is located in the southeast corner of the state, and is the oldest university that was created outside the East Coast in the United States. This is a picture of the campus. We are at the foothills of the Appalachian Mountains. It's a beautiful region with a lot of hills and forest and rivers, so you can do a lot of outdoor activities, and it's a very cute campus, a very beautiful campus. It has a lot of European style buildings, which is quite unusual for Midwest towns. So if you have any at any moment the chance to come and visit us, please send me an email and I will be glad to take you for a little tour in town. Okay, so that's about Athens, Ohio. So what is the outline of my talk? This is basically the list of topics that I will tell you about, and I organized the talk basically in two parts. One part that is focused on covering the introduction to graphene structure and lattice model and the theory models that we use to represent the electron dynamics in graphene. And the second part that is focused on how these dynamics and how the distribution of electronic charge changes when you modify the membrane, the graphene membrane, by applying a strain. I will introduce some ideas on how this strain is represented in the theory models, and then I will talk a little bit about some potential applications, why these things will eventually be useful. So it's my understanding that probably many of you do not have a background in graphene or in fact, in solid state or condensed matter. So if there are, as I said before, if there are things that you don't understand or you would like more detail, please let me know and I will gladly answer your questions. So, basics of graphene. Graphene is a material made of carbon atoms, and carbon, as many of you may remember from your chemistry classes, has these 6 electrons in the last shell, in the valence shell. 2 of them are in the 2s orbital and 4 of them are in the 2p orbital. When you put many carbon atoms together, they create bonds. These electrons that are in these orbitals create bonds in order to establish the connection that makes possible the crystalline structure. So when we draw graphene as a set of hexagons, what we are represented here with each sphere is a carbon atom, and these straight lines represent a particular type of bond that goes under the name of sigma bonds, and it's made up by hybridizing electron states that are in the 2s and in the 2p orbital. Now, the p orbitals that are involved in the sigma bonds are what are called the px and py, choosing a particular reference frame in real space, and the hybridization is known as sp2 hybridization. And these orbitals here are the ones that, represented by straight lines, are the ones that give the material its strength, because these are covalent bonds. The electrons are shared between the 2 carbon atoms, the 2 adjacent carbon atoms, and it's a very strong bond. It's very difficult to deform that bond. Now, there is a remaining, as I say, these orbitals contain the electrons in the 2s and 2 of the 3p orbitals, and there is 1 extra orbital that can host 1 electron, that is the pc orbital, and this orbital forms what are called the pi bonds when you put the atoms close by, because this orbital and this orbital overlap, although in this figure they don't seem overlapping, but in the real structure they overlap, and they are the bonds that contain 1 electron per atom, and these electrons are free to jump from carbon atom to carbon atom. They are mobile along the lattice structure, and these are the ones that are responsible for all the electronic properties that have been observed in graphene samples. Now, once a crystal is created, is put together, we describe the crystal using 2 lattice vectors. Basically, the idea is that you choose a unit, and moving the unit in these 2 directions, with these 2 lattice vectors, you can reproduce the whole lattice structure. These are the A1, A2 lattice vectors. And if you notice, this structure is very peculiar because each atom here is connected to other 3 atoms with an angle, a bond angle of 120 degrees by 3 vectors that are known as the nearest neighbor vectors. Now, these vectors connect, as you see, a carbon atom that is colored with the color green here, with a carbon atom that is colored with the color gray. And the fact that these atoms are colored with different colors is done in purpose to emphasize the fact that each atom has a different neighborhood around it. As you see, this green atom sees 2 atoms in the top and 1 atom in the bottom. However, if we see it in a gray atom, we have the reverse situation. We have only 1 atom on top and 2 other atoms at the bottom. So the fact that these 2 atoms see a different surrounding, a different environment, makes necessary to describe all the electronics in graphene in terms of what happens to the electron that is sitting in this atom. Remember here, let's say the electron coming from this orbital, and what happens to the electron coming from this other orbital who sees a different environment, okay? Normally, we take the 2 atoms as what is called the unit cell, that is a stamp, that if we repeat this stamp following the direction of these 2 lattice vectors, with these 2 atom stamp, we are able to reproduce exactly the whole graphene lattice. So, How do we describe the electron dynamics in graphene? Well, most likely you are not familiar with what is known as second quantization formalism, but this is the basic tool that we use in theory to describe the dynamics of electrons in graphene. So let me see if I can give you a brief introduction, and you can start with this intuitive picture and follow the results that come up from the model. So the Hamiltonian, which is representing the energy function in a second quantization formalism, is written in terms of operators, which are represented by the letter C here. The operator Ci dagger is used to represent the creation of an electron inside I, and the operator Cj is used to represent the destruction of operator of an electron inside J. So this product here is representing the motion of an electron in real space from site J to site I. That is, the electron jumps from one atom to the neighboring atom, or from one atom to two atoms farther away. That depends on the distance between these two. In graphene, we only consider, in the simplest models, first nearest neighbors. So going back to this picture, if the electron jumps from here to here, we say that the electron is destroyed here and is created there. So this is a very convenient formalism to describe electron motion because it directly represents where the electrons are in real space. Now, this jumping costs some energy. This is the kinetic energy of the electron, the kinetic energy of motion in the electron, and the value of that minimum kinetic energy to move from atom to atom is represented by this constant T that has the value of 2.73 electron volts. Now, as I said, the sites that the electrons visit when it jumps are what we call the first nearest neighbor sites. That is, if it is in a site A, let's say it's one of the sublattice, if I label the sublattices by A and B, if the electron is initially in sublattice A, then it will jump to a site in sublattice B. Remember that the green goes to the gray and the gray goes to the green. So when the electron jumps following first nearest neighbors, it changes these two sublattices. Okay, so the hexagonal lattice in condensed matter is not what is known, it does not belong to the classes of Bravais lattices. That is, Bravais lattices are lattices that you can repeated patterns that you can create by repeating a particular stamp, a particular drawing. If we try to do that, let's say, if we choose the green atom as the pattern to repeat, you will see that by choosing the A1 and A2 vectors, we will only be able to repeat the green atoms positions, but we will never repeat in this picture, the violet atoms. And in the same way, if we take the violet atoms and try to repeat them following the two lattice vectors, we will not be able to reproduce the whole hexagonal lattice. So that's what we mean when we say that the hexagonal lattice is not a Bravais lattice. However, if we take, as I said before, a unit that contains both type of atoms, and I take this unit and I move it following the direction of these vectors, you will see, you will have to make a couple of drawings to convince yourself, but it's immediate to see that you can reproduce the whole hexagonal lattice using this as a unit cell. The fact that the unit cell requires keeping count of what happens with the electrons coming from these two atoms because of these different surroundings is equivalent to say that, okay, I will need to know what happens with the wave function of the electron that lives in this sublattice, in sublattice A, and what happens with the wave function of the electrons that live in sublattice B. So I can think of these two operators, these two objects that I introduced in the time-binding Hamiltonian as telling me, okay, this will tell me about the wave function. This will contain the information about the electron wave function when the electron is sitting at one sublattice, and this will tell me about the wave function of the electron when it is at a different sublattice. And in terms of wave functions, you will see that this term is nothing else at psi B dagger, psi A dagger, psi B, or vice versa. Now, the fact that we have to keep track of two objects, or two wave functions at the same time in order to describe the electron dynamics, it's cumbersome to do it in this way, because you have to keep track continuously of two objects at the same time. So people very soon realize that it's much more convenient to use a different notation. To keep track of both at the same time, it would be equivalent to keep track of a quantity that looks like a vector with two components, pretty much like the spin. No? When you have an electron and you want to describe not only the orbital motion, not only the spatial motion with the wave function, but you also want to specify what its spin is, you need to keep track of two wave functions, the one that tells you what happens when the electron has a spin up and the one that tells you what happens when the electron has a spin down. Well, exactly this is the idea behind defining this quantity as a spinor quantity, with the exception that here the two components of the spinor refers to the wave functions in real space. The spin of the electron here has not been yet included, the wave function at the two different sublattices. So what I was saying is represented here in this slide by saying, okay, I can think in the analogy with the spin as having this object taking the value 1, 0, and this 1, 0, the 1 is multiplying the wave function for the electron in sublattice A, as I can think of that as a spin pointing up. And I can think of this object being the 0, 1 multiplied by the wave function of the electron at sublattice B as being represented by a spin down. So in this notation, my Hamiltonian now will be represented by a 2 by 2 matrix, because I will need to know what is the matrix element of the Hamiltonian when I have my two electrons, when I have my electrons in the spin up, in the spin down configuration, and when they change configurations going from one to the other, because remember that I mentioned that the electron, when it's allowed to move, when it's jumping, it jumps from one lattice to the other, and in this notation, that is represented by the extra diagonal matrix elements. So this will be the energy of the electron when it is in a site of sublattice A. This other element will be the energy of the electron when it is occupying a site of a sublattice B. And these two will represent the energy of the electron when it is jumping from sublattice A to B and vice versa. Now, how do I solve this Hamiltonian? Well, the mathematics that I need to use is to take this Hamiltonian like that, express the positions I and j in real space as real space vectors in Cartesian coordinates on polar coordinates, and then what I do is I do a Fourier transform. And when I do a Fourier transform, I go to momentum space. And when I do that, and I do the formalism, what I find is that the Hamiltonian ends up having this form, where this function f has this expression. Notice that it has the momentum. I am using, when I do Fourier transform, I am using a basis of plane waves to represent the wave functions. So this is the momentum of those plane waves. And it involves, the expression for the function f, involves the direction of the two vectors that generates or create the lattice, describe the lattice. If I plot this function as a function of momentum kx and ky, this function gives me directly the energy, because to get the energy, I need to diagonalize the Hamiltonian. The energy will be the eigenvalue of the Hamiltonian. And you see the diagonalization is straightforward because it's a 2 by 2 matrix. And the energy is nothing else than the modulus of this function. And the modulus of this function, when I plot it, has this particular form, which probably some of you are familiar, having seen works on graphene. Now, what makes this shape special is the fact that the red part, which is the positive energy, or what we know as conduction band, where the electrons can move freely, touches the blue part, which is the valence band, where the electrons are tightly sitting in their own positions and don't move. They are connected in bonds with the other electrons coming from the other atoms in the lattice. These two conduction and valence bands touch at a series of discrete points. In fact, they touch at 6 separate points. And if we zoom in, what happens near these points, that is at much lower energies than 5 and -5 electron volts, if I look what happens near this 0 energy, what I see is that the relation between the energy and the momentum is linear. These are cones And this is a conical dispersion in which the energy depends on the absolute value of the momentum. Okay? Now, from these 6 points that I mentioned, only two of them are completely different. You can think of these 2 points as representing in reciprocal space, in momentum space, being equivalent to the 2 sublattices that generate graphene in real space. This is one way of thinking about that. These 2 points are usually known as the K and K prime points, and they are crucial to describe what happens in graphene, for electrons in graphene at low energies, because this linear dispersion, you see, is if I cut at processes up to a certain energy level, if I say I'm only interested in processes that occur within, let's say, 2 electron volts from 0 energy, then what I will see is that the electrons in graphene either move on this cone, have a dynamics dominated by this cone, or the dynamics dominated by this cone. But the 2 cones do not cross, they do not interact, they are completely separate or independent. So, if I go back to my Hamiltonian, I said, well, I started with 2 electrons living in a real space lattice, and now you are telling me that if I go to low energies, I have these 2 electrons that could belong or could have the dynamics governed by what happens near one value of momentum, that is K, or what happens with values of momentum near another value particular you call K prime. And that's basically the idea. We say that we are expanding, if you want, when we do this expansion for the function around these points, instead of having 2 electrons, we end up having kind of 4 electrons, because we are saying, okay, I will have the electrons that are in lattice A and B, but whose dynamics have momenta near this K point, or I will have electrons that in real space move in sublattices A and B, but whose dynamics is happening around this other K point, that is in this case K prime. In that case, my Hamiltonian now will have 4 components, because I will have to say what happens with the electron that live in sublattice A but is near point K, and what happens with the electron that was in sublattice B, near the same K point. And correspondingly, I will have to say what happens with the electron in sublattice A that live near K prime and the one from sublattice B near K prime. So my Hamiltonian now will be written after I do this expansion in a basis of an object that has 4 components. Now, when I do the expansion, as I said, the energy has a linear dispersion with the momenta, and this linear dispersion is clearly visualized here, where you see that the matrix elements depend on the linear power of the momenta. You see that it is not a quadratic Hamiltonian. This will not have a Schrödinger equation, because the quadratic Hamiltonian, when I write it as a differential equation, gives rise to a second derivative. Here I will not have a second derivative, I will have a first derivative, and that's what makes the whole difference for the dynamics in this material. So, because the 2 cones, the K and K prime cones, are separated, they are not mixed, it's very convenient to think about this matrix as being written in blocks. This is known as a block diagonal matrix, and this block diagonal matrix has an upper component given by that will describe the dynamics of electrons near the K point, and this lower block that will describe the dynamics of the electrons near K prime point. Now, when I look at the form of this matrix, I realize that because it's a 2 by 2 matrix, I can write it in terms of the sigma Pauli matrices that were introduced to describe the real electronic spin. In terms of the sigma Pauli matrix, the Hamiltonian takes a very, very simple expression. Is this like here for valley K, and this like here for valley K prime. Notice that the signs are different for the momentum along X, and that makes the sigma to acquire a complex conjugation in order to represent exactly this expression. Now, in this Hamiltonian, the basis in which this Hamiltonian is written, or the wave functions associated with this Hamiltonian, again, are a 2-component object, the 2-component spinor, that will tell me about the dynamics of the electrons that have momenta near the value, the momentum K, the big K. While this one will tell me about the dynamics of the electrons living near momentum K prime. The form of this Hamiltonian is formally identical to the one that Paul Dirac introduced when he was trying to, when he described the motion of electrons in the relativistic regime using quantum mechanics. So Dirac was trying to extend the formalism of Schrödinger that was for electrons that were moving at non-relativistic speeds. Dirac extended this theory to the relativistic case, and he found an equation in which the energy was linear with the momentum, or the Hamiltonian linear with the momentum operator. When the Dirac equation is written in 2 dimensions, it takes exactly this form when the mass of the particles is 0. And that's why people say that electrons in graphene behave as 0 mass Dirac particles, because formally, in this expression, the mass term does not appear. And you may wonder why the mass term does not appear. Well, as you notice in these matrices, the diagonal elements are equal to 0. And the diagonal elements corresponded to the energy of the electron when it is sitting at a given sublattice. Now, as it happens, because there is 1 electron per atom, as I mentioned before, there is 1 electron per carbon atom, so I have 1 electron per site in the graphene lattice. When the material is pristine, that is when it doesn't have any doping, any impurity or any defect that changes the number of electrons. If I have a pristine material, at the neutrality point, these 2 quantities are identical, because the 2 carbon atoms are identical even when they are in different positions in real space, and the energy is the same for both, and happens to be 0 energy, exactly at the neutrality point. So the fact that the energy at the sublattice for pristine graphene is 0 is what makes these diagonal elements to be 0, and makes eventually this equation to have no mass. Okay, so this is what is known as the Dirac equation, and as you saw, the Hamiltonian around the 2 different valleys, around these 2 different k and k prime points, looks different. If I write my spinors in this way, the Hamiltonian looks different. But if you remember some of your algebra classes, you say, well, maybe I can write the basis in a different way, in a different order, so I can make the 2 Hamiltonians look the same. So can we have these 2 Hamiltonians look the same? And the answer, yes. And this particular way of writing the basis, this particular way of saying what each component of the spinor is representing, is known as the valley symmetric representation. In this representation, the 2 Hamiltonians, both at valley k and k prime, look exactly the same like the Dirac Hamiltonian, but the price that we are paying to have this is to have to write the spinors in a different way. So around the k point, the spinors look as before, but around the k prime point, the spinors now, the components of the spinor, are representing something different. The upper component represents the wave functions of electrons sitting in sublattice V, around k prime point, with a phase, with a negative sign in front, while the lower component is the one that represents the wave functions of electrons in sublattice A. The wave functions for the Dirac Hamiltonian, when I diagonalize my Dirac Hamiltonian, notice that the Hamiltonian is not diagonal, so in order to find the eigenvalues and eigenfunctions, I need to diagonalize it. And once I diagonalize it, what I find is that the eigenfunctions are a linear combination of electrons in the 2 sublattices with these phase factors, where the angle here, theta, is defined as the angle between the momentum of the electron. The electron is, the wave function of the electron is a plane wave for both sublattices, but for one sublattice, it has a phase that is given by that. For the other sublattice, it has the other phase. And as I said, the angle theta is the angle between the momentum of the electron with respect to a crystalline direction that I label x. In my talk, x will always represent the zigzag direction of graphene. The zigzag direction of graphene is this, okay? So that's how I put x here to represent that, the zigzag direction. The other direction is known as the armchair direction, the perpendicular one. Now, theta then will be the angle made by the momentum of the plane wave with respect to this direction. Finally, the factor S that is here is representing the sign of the energy, because as you saw in this expression, the energy has positive and negative values. This is another characteristic of the Dirac equation. So, with this, I finish basically the essential material to describe with a theory model the dynamics of electrons in graphene. What I am going to do is I am going to work with these objects. I will modify this Hamiltonian, and I will see how this Hamiltonian is modified due to the interactions or the new terms that I will add. I will diagonalize the Hamiltonian using this base, and then I will see what happens with each components of these objects to describe what happens with electrons and each sublattice and with different momenta. So, the interaction that I am going to talk about today is produced by deformations. And we know that being a two-dimensional membrane, graphene is a very easy material to deform. From the very first experiments where they deposited graphene on platinum, and they found out that after deposition, they found that regions where the graphene was sitting on top of little bubbles or mountains. And the bubbles have a very peculiar shape of triangular mountains and have different characteristics of the properties that were measured in the flat regions. In this other experiment, so this is basically when graphene is deposited on top of things and impurities or bubbles are captured in the deposition process. Here is when the material is bombarded, is damaged with ions, and the substrate reconfigurates, and again there is an accumulation of defects that nucleate in local regions and creates these particular blisters that again you see have different shapes. That's why they are circle with different formats, but in general have also a triangular type of shape. Graphene was also easily deformed when it was under thermal treatment, when deposited on the substrate, and it was annealed because the different thermal coefficients of the substrate and the graphene membrane, the material deformed differently, and after the thermal treatment, it was observed the appearance of folds or wrinkles, no? Like when you put a tablecloth on the table and you stretch it and you compress it and you have folds forming on the tablecloth. Well, something like that happened here after thermal treatment. It also happens when you scratch, like in this experiment, that the membrane was scratched with a very, very sharp tip that was creating a trench in the material, and instead of remaining flat or parallel to the surface, graphene automatically bends on itself and starts peeling off to create these ribbons that grow on itself because of the bending, the easiness of bending that the material has. And the most trivial way of seeing deformations is when you have the material suspended. In all these cases, the material was on a substrate, but when you have the material suspended and you stretch it, and you see that there are these modulations. This is bilayer graphene, this is monolayer, and you have modulations. These are measurements of the different heights that the membrane has in different positions, and you see that you have periodic modulations. The material goes up and down, up and down. These are ripples that form under strain, and that in bilayer graphene are visible with plain hindsight, with plates in plain sight. When you see these linear horizontal lines there representing wrinkles form, that is when you, for instance, take your tablecloth or a plastic wrap and you stretch it, you immediately see folds forming in the transversal direction to the direction tensing the material. Finally, the material being so light and so easy to deform was found to be deformed by tips of instruments like the scanning tunneling microscope that is used to create images of surfaces. And let me spend some time telling you a little bit about this experiment. In this particular experiment, graphene was deposited on top of silicon dioxide. Silicon dioxide is a material that has a lot of rugosities on its surface, so it has a lot of hills and bumps and throws. And when graphene is set upon this material, what happens is that it follows some of the rugosity, some of the corrugation, but not perfectly. So this Professor Morgenstern, who was the person leading the experiment, wanted to know what was the effect of these corrugations in the STM images, in the scanning tunnel microscope images of the material. So he started to take measurements in different regions of the membrane, and what he found were regions where he saw hexagonal shapes here, and the side of these hexagons changed very little from place to place. You see it change from 0.25, the distance between two carbon atoms, which is known as the lattice constant, from 0.25 to 0.22 in different regions of the material. And let me add that he saw practically perfect hexagons, and in this technique what you are seeing is the distribution of electronic charge, and you expect to see hexagons because if you remember, the hexagons are the lines that form the hexagons are representative of the distributions of electrons. They are equally shared by the two carbon atoms, so what you expect is that they are shared along these sigma bonds, this structure given by the sigma bonds that describe the graphene lattice directly. The thing that was surprising for him was that in certain other regions of the material, he found pictures that were not hexagonal at all. They look more like triangular pictures, as you see here and here. And they have different corrugations, much smaller corrugations. They have a shorter wavelength. They existed in much smaller regions. And he assumed that this was because there was an underlying strain producing changes in the charge distribution that was causing these STM images. So what we set up to do was in our group was to try to make a connection between the charge distribution that he was observing these images and the strain that could occur if you deform, that is, if you separate the carbon atoms from their equilibrium positions. We wanted to see if there was a relation, and if that relation was the cause of these dramatic changes in the STM images. So what we did was to say, okay, well, let's imagine what happens when you deform graphene. And when you deform graphene, what happens is that you basically are changing both the length and the angle of these nearest neighbor vectors, because you are changing the atomic positions of the carbon atom. So for a given atom, the other three that surround it as nearest neighbors will be located at different positions. So for instance, this atom here will be displaced by a vector u1, 1 prime. This atom here will be, this one here will be displaced, and this one here will also be displaced. So in general, the nearest neighbors to a given atom in the lattice will be now given by, or at the distance given by the modulus of this vector, which is the original distance plus a new term. And this term is described in terms of the elasticity tensor. So when we deform a material, we describe the deformation in terms of the new positions of, in the case of a crystal, the new position of the atoms in the crystal. In the case of a continuum material, the new positions of the different points in the material. So in elasticity theory, we describe the changes in these positions with a quantity that is a tensor that has two indices and is known as a strain tensor, and is described in this case by how the in-plane positions of the atom change, and that's why it's a derivative. So it's the change in the in-plane positions plus a term that is a change in the out-of-plane positions. That is, if the material is a membrane, the atoms could be moved in the plane where they are located, which is what happens when you apply a tensile strain or a compressive strain, where the material keeps being in a flat surface, or the atoms can be moved in a third dimension, right? Can be get a position out of plane, and how the position changes out of plane is described by this term in the elasticity tensor, in the strain tensor, sorry, in elasticity theory. The difference between these two first terms with this one, as you can see, is that this is nonlinear. This is a quadratic term in the positions of the atoms, while these two are linear in the positions of the atom. So that makes a big difference because this introduces nonlinear effects into the theory. So how does this enter into the theory? Well, in the tie-binding Hamiltonian that I introduced earlier, this distance tells us how easy it is to move one electron from a given atom to its nearest neighbor. So what we expect is that if we change this distance, it will be different. The amount of energy that we need to move the electron, it will be different. So it will be encoded into now a coefficient, that now I call Tij, because it will depend on the positions of the two atoms that I am considering, the electron moving from and to. So that's why I added the labels Ij. And if I think about this as the energy, well, the energy basically will be the overlap, given by the overlap between the initial wave function and the final wave function with the Hamiltonian in the middle. And because it's a wave function of an electron that is localized in an atom, I expect this wave function to have an exponential overlap with another wave function, with the wave function of the electron in the other atoms. And if I am changing the distance between these two atoms, the change in this quantity will also be exponential. So when you go through the formalism, you realize that you can write exactly the new kinetic energy of the electrons under these deformations as the original one times an exponential factor that depends on the new distance between the atomic positions, and a factor that is characteristic of the coupling, the interaction between the electrons and the ions in graphene, and that because it's in graphene, takes a value of 3. This quantity depends on the material. That's what I want to mean. So the interesting thing about this change, is that you can think of if this quantity is small, you can always think of exponential in terms of its Taylor expansion. You can think that you can write exponential as 1 plus something. And when I write the continuum model, when I do the expansion around the k and k prime point, this t appears in a very particular combination of terms that I can write as a component of another quantity, which is this Ex and Ay. Because the Ax and Ay, it's a two-component object, it's very tempting to think of it as a vector object. In fact, it's not a true vector because it doesn't transform under the symmetries that the system has as a vector could transform. But it looks pretty much like it. And because it looks pretty much like that, we refer to it as a pseudo-vector. Because of the way that it enters into the Hamiltonian, this plays the role or looks like a pseudo-gauge potential, a pseudo-gauge vector. And this is exactly how it enters at valley k and at valley k prime. You see, the fact that it depends on the positions of the nearest neighbors, and the fact that, as I mentioned, each atom sees a different arrangement of nearest neighbors, the changes in the nearest neighbors for this atom will have to be somehow related to the changes seen by this atom, but taking into account this change of environment, this thing is what produces that this combination appears with a plus sign for the Hamiltonian in valley k and with a minus sign from the Hamiltonian in valley k prime. So this Hamiltonian looks like the Dirac Hamiltonian for massless Dirac particles, linear, in the presence of a gauge field. Now, if this gauge field were to represent a true magnetic field, the sign would be the same for both Hamiltonians. However, the fact that it enters with different sign is telling me that it's not representing the true magnetic field. And besides, in order to represent a magnetic field, this quantity needs to have a curve, right? So it needs to have derivatives because the definition of a magnetic field is given by the curve of the rotor of the gauge field. And this means that this thing needs to have derivatives different from zero in order to produce a gauge field, a magnetic field. So this thing is nothing else than how these new hopping terms, this new kinetic energy from atom to atoms are changed when we have a strain, and in particular are given by the components of the elasticity, the strain tensor, in this way. And if these components change in space in such a way that the derivatives are different from zero, then I will have the electrons moving under an effective pseudo-magnetic field. And again, the word pseudo comes because it's not a true magnetic field. So what I am trying to say here is that when we apply a strain in a graphene membrane, the way that the electrons feel that strain, feel the change in the positions of the carbon atoms, is equivalent to have them sitting in the presence of a gauge field that, if it depends on space, on the different positions in the lattice, it is completely equivalent to have the electrons moving in the presence of a magnetic field. So that connection allows us to create intuitive pictures of how a strain modifies the motions of electrons, because we know how electron motion changes when we apply a magnetic field. We are all familiar with the classical physics of the Lorentz force and how the electrons form circular orbits. And if we go to a quantum description, we know about Landau levels and all that theory that is well developed. So the fact that all these mathematical transformations, and it may seem like tricks many times, allow us to create this connection facilitates a lot our interpretation of measurements. So here I listed many other changes that the strain introduces, and that I will not go in detail because I checked the time. I am running late already, but I just wanted to let you know that this is the effect of a magnetic field appearing as representative of the strain is not the only effect. There are other effects that also modify the electron dynamics, and in a given situation you have to evaluate how important they are with respect to the presence of the pseudomagnetic field. So a summary of the introduction is that the electron dynamics in graphene physics can be represented by a Dirac equation for two separate valleys, k and k prime. It's a massless Dirac equation. That's why electrons are considered to be like photons, and it's necessary to carry to keep into account a quantity that is a pseudo spin that represents what happens with the electron sitting at each sublattice in real space. And finally, the effect of a strain in the context of this talk is represented by a pseudomagnetic field, and this is expressions of the two Hamiltonian. Okay, so let me now go to applications, and I will go fast here. So the first application that we studied was to say, well, let's try to see if we can connect the deformations that we're observing the experiments done by STM tips with a model that mimics or tries to represent the presence of a bubble in a graphene membrane. So we said, let's start doing a tie-binding Hamiltonian that in real space, where we can put this Hamiltonian write a code to represent this Hamiltonian and solve it numerically. And let's represent the deformation that is produced when it is measured, or for the graphene sitting on top of an impurity or a compound when it's deposited on a substrate. Let's represent that by a Gaussian shape, okay? Now, with a Gaussian shape, we are able to describe, with this shape, we are able to describe the positions of the nearest neighbors for each atom in our discretized lattice systems. And with these positions, we are able to calculate this Tij, and then we diagonalize the Hamiltonian using standard numerical techniques for this type of problems. And we calculate the density of state, which is nothing else than the charge distribution that happens for this particular system. And what we see is that it doesn't matter in which orientation we put the graphene lattice with respect to this Gaussian bubble. We see that there is an enhancement of the density of state in regions that have the shape of a flower with 6 petals. You see 6 petals with one orientation at different energies, and 6 petals in a different orientation at different energies. So what this is saying is that for a wide range of energies, here we are going through a range of 100 millielectron volts to 150 millielectron volts. And you see that in this region of energy, here is even wider, we see a charge accumulation in particular regions of the sample, and charge depletion, the density of state, the number of electrons in the white areas has been depleted, is 0, because these electrons have moved to these regions. And these regions have the size of the bubble diameter, basically. They have the size, roughly, of the width of the Gaussian at half height. So we said, okay, but this has a shape of 6 petals, and this will give me an hexagonal symmetry, a perfect hexagonal symmetry. So I would have expected to see in the STM images a perfectly defined hexagon, something that has a 6-fold symmetry. However, what was observed was a 3-fold symmetry. So how can I see that? So what we did, because we have the Hamiltonian written in terms of this pseudo-spinor, was to see what happens with the wave function of the electron sitting at each sublattice separately. And here, you will see that I have drawn triangles up and down to represent the 2 sublattices. So let's focus, for instance, in this hexagon here, where I have 6 triangles, 3 of them pointing up that are white, and 3 of them pointing down that are dark. The darkness is telling me that I have more electrons sitting there. And you see that the electrons are selectively sitting in the triangles pointing down. So they are sitting in one sublattice, while in the other sublattice, remains empty. Now, if I move to another region of the sample and I go here, I have another hexagon where the triangles that are dark now are the ones pointing up. So what this is saying is that the charge is accumulated in these regions. Clearly, I have the 6 petals here, as I saw before, but in each petal, the charge is even distributed inside each petal between the 2 sublattices, with one sublattice being much more occupied, having more electrons, hosting more electrons than the other sublattice. And this occupation alternates from petal to petal. So here I plotted the electron occupation, the electron density per sublattice, and you see clearly that one sublattice is clearly occupied while the other is empty, and respectively for the other sublattice here. So the fact that the charge is redistributed in this particular shape tells me that if I am taking an STM image here, I will see only the carbon atoms that host the electrons, and in this case will be the carbon atoms belonging to only one sublattice. While if my STM tip is in a region like this, I will see the other sublattice, but in both cases, I will see only one of them. And that is what happens in these experiments, where the tip is precisely measuring or taking images in one side of the bubble. And that's why, while in the flat regions, you expect to see perfect hexagonal images, in one side of the bubble, you start seeing only triangular regions. So we did the model, we solved the model numerically, we solved the model in the continuum limit, that is using the Dirac Hamiltonian and using the matrices that I was referring to at the beginning and the Dirac equation, and we were able to come up with a formula, with an equation that can predict what is the difference in contrast between the image taken for one sublattice in the deformed region versus the pristine region, and the formula was compared to the experimental data, and we got a pretty good fit. Besides learning learning that the contrast depended on the height of the deformation, and the maximum contrast occurred at the distance from the center of the Gaussian at half height, the maximum of hub height. That's where the maximum change in the density of state, the maximum charge accumulation occurs. So basically what I am saying is that these deformed regions trap charges pretty much like a quantum dot, accumulate charges, and these charges are distributed in a very, very peculiar fashion. So the experimentalists did this movie that I cannot share. I cannot share this movie. No, I cannot share the movie. Okay. If you visit the paper, the reference, I give a list of references at the end of this reference here. If you go at this reference in the site of Nanoletters, there is a video. This is the one that I wanted to show you that shows exactly how the STM image is taken and how the way that they take the image ensures that they are always taking data on one side of the petal. Okay, so this is the quantum dot part. We can do something similar for extended deformations, for ripples and folds. And in this case, the shape of the membrane looks like this. And if I look, if I represent the shape with a Gaussian, I again can repeat the procedure that I told you before and obtain what is the form of this gauge field. And this gauge field changes in position, so gives rise to a pseudomagnetic field. And here I plotted the profiles of the pseudo gauge field and the magnetic field. Now, the fact that the pseudo gauge field has a double barrier structure makes it easier. This is a picture of how the pseudo field changes in position, and you see that it alternates colors. So the fact that the gauge field has a double barrier structure makes it easier to work with Hamiltonians in the continuum limit, as I mentioned before, because I have explicit form for the Gaussian, the gauge field, and I can try to attempt a solution not only numerically but also analytically. Notice that the field has a double barrier structure, and double barriers, well, these are problems that I have been working with in quantum mechanics when I was introduced to quantum mechanics the first time, right? This, I can think of a double barrier potential. If my gauge field has the form of the double barrier, I can think of having as an approximation these barriers to be square barriers. And if I want to know where the electrons, how the electrons are modified by this presence, well, the only thing that I have to do is calculate wave functions for a double barrier structure. And this is basically what we did, starting with one barrier. And first we look at what are called extended states, that is plane waves. So we put a combination, we started with one barrier first to make it easier. And we said, well, in region 1 and region 3, we will have a combination of incoming waves and outgoing waves. And in region 2, we will have a different combinations of waves. Notice that this is a two-dimensional problem, but has translational invariance along x. So that's why the sign of the momentum in x doesn't change. These are plane waves along x in both cases, while the momentum in y is the one that is modified due to the barrier, the presence of the barrier. So basically, what we do is a single barrier potential, and we calculate the transmission for the single barrier doing the single barrier potential, and you see that the red represents states that are extended states for different angles of incidence towards the fold, states from valley K and K prime, and there are regions where they do not overlap. So if I create a wave packet with electrons that have momenta from both valleys, and I make them to be incident in a fold at a certain angle, let's say at an angle of 30 degrees, well, the states that are coming from valley K will have transmission 0, while the states that have in the wave packet that come from valley K prime will have, at different energies, will have finite transmission 1. So after going to the other side of fold, I will have states from one valley only. So given the time, so I am showing here results for the double barrier, and very similar to the other, the resonance is split. But what I want to point out is that these are states that are all plane waves. No, they are all plane waves, all imaginary exponents. So we ask can this structure also behave like the quantum dots, creating localized states? And to create localized states, what we need is to have a momentum that is imaginary in this region. So we look for them, we look for evanescent waves that die inside the barrier, and effectively we find states that have energy versus momenta that come with a discrete spectrum, and these are localized in the barrier. These are the wave functions for the states located here in this signal by this square, and this is the wave function for the state that has this momentum and this energy, and you see that the wave function of this state has an exponential decay outside and inside the barrier, and it's located precisely inside the barrier. This plot shows the state in this, represented by this rhomboid here at this momentum and this energy, and the wave function also decays exponentially outside the barrier. It lives inside the barrier a little bit. It's not only at the edge, but these states are confined by the fold. So the fold has has the same feature that it's able to localize states in the vicinities of its edges and inside the fold. So we check what happens if the shape is not Gaussian, what happens if the shape is not symmetric, and in all these cases, we find that folds are able to confine and at the same time are able to contain extended states that move along the fold, and that's what we call wave guiding. So these features are exploited for Valleytronics, and sorry about that, but I will skip this. And I want to finish acknowledging all the people who have worked on this problem along the years with me, and this was a literally multinational collaboration with people from Brazil, from Mexico, from Germany. Dawe was my student until 2 years ago. He's now a postdoc at the University of Hong Kong. And Tarek is my current student, who is from Bangladesh. He came to us with a master from the University of Dhaka, and he's working on extending these ideas to periodic structures in which we have a periodic distributions of folds, of bumps. And these are the people who were involved in the experiments that we were able to help understanding. And with that, I finish. So,
thanks,
sorry
madam,
for extending.
wonderful presentation. So if you allow, we can start our discussion session. So I have got a few questions in inbox. So if you allow, I can start reading those. So how do we can deform graphene?
Okay, there are two ways to deform graphene. One, if you deposit it on a substrate and the substrate has bumps and hills. So graphene, it's very flexible, but it has some rigidity. So, so it will follow the substrate as much as it can, not necessarily if the fold, for instance, is very sharp, graphene will not adjust so sharply to the edge. It will hang a little bit on the throw, but it will follow the rugosities of the substrate. Another way is to pattern the substrate, to have a substrate that is flat and to build like little bumps, or people these days are putting cylinders, periodically spaced cylinders, and they create like a bed with these cylinders, and they deposit graphene. And if you see when the separation between these two cylinders is big, graphene gets hanging in the middle. So it has blah, blah, something like that, and it's the form. Another way to deform graphene is suspending it, so grabbing the graphene and attach it to two contacts and separating the contacts. Another way is to deposit graphene on a material that has been perforated, so graphene is on a hole, and people put gas in the hole and they inflate and create a bubble. So there are many, many different ways that we can deform graphene. We are working these days on graphene deposited on pattern substrates, because a pattern substrate allows you to control the type of deformation that you have and then to design the property that you want.
Thank you, madam. So we have another question. So is there any application of deformed graphene in astrophysics?
That's a very good question. I don't know. I know that they are looking at graphene and other two-dimensional materials to improve the resolution of the detectors in different energy regions. Maybe as a sensor, the deformations can be used because the charge distribution, as I show, is so sensitive to the strain. If, let's say, I don't know, a sensor is able to, if we can build a sensor by the changes in this charge distribution, if graphene is deformed when it's impacted by an optical signal, that would be one possibility. The electron dynamics, when it is irradiated with light, also changes in graphene. It's not linear anymore. And yeah, I can imagine that by looking at different radiation, terahertz radiation, which is very low energy, graphene would be able to be sensitive to that. Those are ideas.
Thank you, madam. This may be the last question. So what is the graphene flake?
How is a graphene flake made? Sorry, yeah. I didn't. Well, originally people, the first, people have been trying to isolate graphene for many years. The ones who were successful were putting graphene on a Scotch tape, and they were closing the Scotch tape, and probably you're familiar. There are a lot of YouTube videos about this procedure online, but the idea is that because graphite, the material, is made out of these graphene layers that are very loosely attached, because the bonds, the electronic bonds between the layers, is a van der Waals bond, which is weak. So it's very easy to separate them. And the fact that they were gluing and ungluing the Scotch tapes, they were able to separate a piece of graphene. The problem with this way of making a flake that is a finite sample of graphene is that it's completely uncontrolled, the size of the flake that you end up having, the type of termination, and also the purity, because you may create defects in the middle of the flake. So people have been developed other methods to grow graphene. The one that could have potential applications is made with a technique called CVD, chemical vapor deposition, that creates in reality more polycrystalline samples. That is, different graphene flakes that are attached to each other but have different crystalline orientations.
Thanks, madam, for your wonderful presentation and discussion session, madam. So the main aim of our program is to motivate and encourage our students in this corona pandemic situation. So we are very grateful to you that you have given us time from your busy schedule for our students. So thanks again. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for giving us time. So
okay, thank you very much. And if you have any question, please contact me, and we'll be happy to respond. Thank you again.
Yeah, bye for today. Thanks.